Thank you. Okay, hi everyone. So yesterday we worked. So I'm gonna start without the microphone, but you should complain if you cannot hear me. I should use the microphone? Okay, I will use the microphone. Okay, good. So yesterday we worked very, very hard. And of course the purpose of working very hard is so that you don't need to work very hard anymore. And you can just relax and get everything for free. So that's going to be the plan. I mean, after we finished all this hard work, we have some very powerful tools, and then we can get lots of results very, very easily. But we have some bits and pieces that we still need to complete that I didn't quite finish yesterday. So the beginning of today is going to be a few minutes of completing these pieces. Then we'll talk very, very briefly about the MSSM. And then we're going to go on to the topic of the remainder of these lectures, which is dynamics in supersymmetric theories. And I'm going to be cheating a little bit because originally I said that today's afternoon session will be Q&A and exercise solving and things like that. But I decided that that's not such a good idea because it would be more useful to actually talk about some of the mediation of Susy breaking in the standard model in the MSSM. And that's going to be very light because it's essentially phenomenological. There's not going to be a lot of technical stuff, and anyone who wants to really work through the exercises can do that at their own time. So I think this is going to be a better use of the time. Okay, so we've seen lots and lots of things yesterday, and now we can put it all together. So essentially for chiral fields, for chiral superfields, we already know how to write Lagrangians, and the prescription is the following. So there's the part coming from the Scalar Potential, which depends on the phi's and the phi daggers. There can be a bunch of them. And then there's the superpotential part that we talked about a lot. This guy only depends on phi, it doesn't depend on phi dagger. And there's the complex conjugate here. Whereas this part is real. This is a real superfield. Now, we said that the canonical Scalar potential is just phi I dagger phi I, sum over everything. And now the thing that we need, of course, is we want to know how to add Gage interactions. And so if we, or Gage symmetry, I should say. So if we have a U1 Gage symmetry, instead of writing this scalar potential, what we should write is phi I dagger e to the QIV phi I, where V is the superfield that we wrote yesterday. And if we have an SUN symmetry, then the thing that we write is phi I dagger e to the V phi I, where this V is VA TA, where TA is the generator, and VA is the real superfield that we wrote down yesterday. Now, let me also complete something that I think I probably didn't stress enough, which is that, remember that we had this example with the phi plus and phi minus and their attendant fermions, and we wrote down a superpotential of the form phi plus, phi minus. So here the point is that if I wanted to introduce a U1 symmetry such that these guys are charged, and this has U1 charge plus, and this guy has U1 charge minus, then you see that this is the only superpotential I can write down. Because this has charge plus, this has charge minus, the whole thing is neutral. So that's very, very different from a non-supersymmetric theory. In a non-supersymmetric theory, I can always write down m squared phi plus squared, and similarly for phi minus. But here I'm not allowed to write down any phi daggers in the superpotential, and so that's why we have this form. Okay. Now we can write down the full Lagrangian containing also the Gage symmetry. So let me do it over here. So this is the Gage theory Lagrangian. So I have first of all d for theta phi I dagger e to the v phi I plus d squared theta w of phi I plus the complex conjugate. And of course this guy needs to be a Gage invariant combination of the fields, just like we said now. And then these different pieces, so that's 1 and that's 2, and if we start to work out each one of these pieces in component forms, we're going to get the following things. First of all, from here, what are we going to get? We're going to get to the kinetic terms for the for the phi i's. Let me denote maybe. Let me use big phi to denote the chiral superfield, and phi I, a small phi I, to denote the scalar. So these are the superfields. So we get kinetic terms for the scalars and for the fermions. And we also get Fi squared terms. This guy we talked about a lot, so I'm not going to write down the things that we get from here. But there's a third piece that we need, which is the Gage kinetic term. So what's in the Gage kinetic term? So in the Gage kinetic term, there's the minus a quarter f mu nu, the usual thing. But of course, there's also a Gageino now, so you need to write a kinetic term for the Gageino. And there's also 1/2 dA, where this is the auxiliary field. So these are the fields that we saw yesterday. We saw that when we go to a Zumino gauge, we're just left with a vector field. So this is the field strength, the usual thing, the Gageino, and the auxiliary field D. So that's how they appear in the kinetic part of the Lagrangian. Now, you could take just this piece, and just as we did originally, you could check that this piece of the Lagrangian is supersymmetric on its own. But we can also derive it in superspace language. So let me just give you the result for that. So how do we write this thing in in superspace language? So we can introduce a superfield of the form that we're going to call W alpha A, which starts out with the Gageino as the lowest component, minus sigma mu nu theta alpha Fa mu nu plus theta alpha dA. And I'm not going to show this, but actually you just get this by acting with some derivatives on the vector field. Just like you get the field strength, the usual F mu nu by starting with a Gage field and applying some derivatives, one derivative. It's kind of an analogous thing over here. And then the Gage kinetic piece in the Lagrangian is coming from d squared theta W alpha plus the complex conjugate. So that's just how this part appears in superspace language. And you see that it's kind of analogous to the superpotential because it's a d squared theta term that we're taking. So this is a chiral superfield. Okay. Now, in some cases, it's going to be different to choose a different normalization. So remember that there's always sometimes it's more convenient to write the kinetic term like this, and sometimes it's more convenient to put a g squared in the denominator. So there's exactly the same issue here, and we're going to sometimes work this way and sometimes work the other way. And so instead of writing this, very often we'll want to write the following thing. So there's this here for convention, essentially, d for x, d squared theta, tau, wa alpha, plus the complex conjugate, where tau is a complex coupling. So it's 4 pi I in these conventions, 1 over g squared minus I over 16 pi squared theta. And in order not to confuse this theta with the Susy theta, I'll call it theta Young-Mills. That's the instanton theta. That's the axion theta, I'm sorry. So when we work this out in component form, what do we get? We get that L Gage has the following pieces. There's d for x minus 1 over 4g squared f mu nu minus theta Young-Mills over 32 pi squared. I forgot the a here. Fa mu nu f tilde a mu nu plus the piece that has the Gaugino lambda in it, and I don't want to write down, plus 1 over 2 g squared dA. And f tilde a mu nu is epsilon mu nu rho sigma Fa rho sigma up to a factor of 2. So this tau, this coupling that we have over here, is usually called the holomorphic coupling. And you see why. It's the thing that appears in the holomorphic part of the Lagrangian. If we want to go to canonical normalization, then we have to take the Gage field, A mu A, and rescale it by G, and then we have something that's canonically normalized. Questions about this? Okay, so there is one other thing that I want to mention before we go on. And this is the R symmetry. So if you look at all the examples that we wrote down, all the different Lagrangians and superpotentials and so on, you'll see that there was always a U1 symmetry that was hiding in there, and we didn't talk about it. And this is a completely normal U1 global symmetry, but it's called the R symmetry, and it's a symmetry that doesn't commute with supersymmetry. That is, different components of the same supermultiplet carry different U1 charges. So if you just go and look at any of the Lagrangians that we wrote down, you'll see that this U1 is really there. So for example, if I look at the chiral, any chiral superfield, there's the scalar part, there's the fermion part, and there's the auxiliary part, and if this guy has charge Q under the U1R, then this guy has charge Q minus 1, and this guy has charge Q minus 2. So you see that this is as if theta is carrying charge plus 1 under the R symmetry. And then you see that this is consistent with saying that the superpotential, so in the Lagrangian, for example, we had to take the theta squared component of W, and so this is consistent with W having charge 2. Similarly, if I look at the gauge field, in the gauge field, I can look, for example, at W alpha, which started like lambda alpha, and then there was some theta piece and F mu nu. So this is just a normal derivative times V mu. So if I want the gauge field to be neutral under this U1 symmetry, then lambda has charge 1 and everything is consistent. Okay, so you can just go through all the examples and convince yourself that this symmetry is really there. Okay, and if you're used to thinking about the MSSM and you hear about R parity, then R parity is just the remnant of this U1R global symmetry. Okay, so now I want to talk about the MSSM very, very briefly, because I think this is something that's kind of easier to complete on your own, but let me emphasize certain things. So we take the standard model and we supersymmetrize it. That is, we just impose supersymmetry, and we get the MSSM. That's the minimal supersymmetric standard model. And when we do that, there's absolutely no freedom. Everything is completely dictated. There's nothing that's up to us. So the first thing that we need to do is we need to embed all the fields in supersymmetric multiplets. So think about the fermions, for example. So I have quarks. Let's say I take the up quarks. So they transform like this under the standard model gauge group. I have my fermion Q. Then I should embed it together with some scalar Q, the fermion Q, and add an auxiliary field, FQ. Okay, so this is the scalar. This is the original quark, and this is what we call the squark. And I should do this for all the fermions of the standard model. Then there's the gauge bosons. So for the gauge bosons, it's the same story. We take G mu A, for example, the gluon field, and we put it together with the Gageino, lambda A, G mu A, and add an auxiliary field, dA. The remaining piece is the Higgs. So the Higgs is a little more tricky. So we take the Higgs and we embed it again into a chiral superfield. So we have the Higgs, and I'm going to call it H down for reasons that we'll see in a second, the Higgsino, and there's also an F term that I should add. But then what's the problem? The problem is going to be that I won't be able to write down Yukawa terms for everything. Because remember, in the standard model, the downs get Yukawa couplings with the Higgs, and the up quarks get Yukawa couplings with essentially the Higgs dagger. And I'm not allowed to write daggers in my superpotential, so I need to actually double this guy. So there's also an H up Higgsino, and let me call it FH down and FH up. And this is as far as the fields go. Then we also have the Yukawa Lagrangian, and this is now coming from the superpotential H up Q UC plus H down Q DC with some coefficients that are the Yukawa couplings that I'm not going to write. But essentially, that's the whole story. And there's absolutely no freedom here. I mean, the couplings that appear here are just the standard model Yukawas, and that's it. Now, of course, the other thing that we need is we know supersymmetry is broken. So we need supersymmetry breaking masses for all of the superpartners. So we need now supersymmetry breaking masses. Now the rule, we already said this, is that if we have some source of supersymmetry breaking, then no matter what we do, we're going to get supersymmetry breaking masses for just the right guys. The fermions are not going to get mass because they're protected. The Gage bosons are not going to get mass because they're protected too. And very often you hear people say that this is really very ugly because we need on the order of 100 parameters, and you need to generate all these other, and you need to write down all these 100 parameters. But this, of course, is complete nonsense. I mean, if the idea was that we would write this Lagrangian and then have to introduce masses by hand for each one of the superpartners, this would really be ugly, but no one would want to think about this. So the point is that in any sensible theory, we have some source of supersymmetry breaking, and that determines all the masses. And all these 100 masses can be, can usually depend on very few parameters. There's even one scenario where they depend on just one new parameter, and that's it. So the only trouble is that this particular scenario doesn't work, but let's put that aside for a second. But the point is that all these parameters are generated by very few things, and the picture is roughly like this. So the nicest thing would have been if you took this, if you took the standard model, supersymmetrized it like this, looked at the potential. So of course this is the superpotential. I can write down the scalar potential from this, and maybe I would get supersymmetry breaking for free, just like we did in the O'Rafferty model. But that doesn't happen. I mean, we actually already know that it doesn't happen. How do I know that it doesn't happen? Like this at tree level. So what do I need for supersymmetry breaking? I need a scale. And so far I didn't write down any scale. So I cannot break supersymmetry. Now that's a little naive, as we'll see in a second. But at tree level, this is really true. But the point is that I need to add some new stuff to the standard model, to the supersymmetry standard model, and then I have some Susy breaking sector, and then the SSM. So what is this thing? This is a bunch of fields and interactions that break supersymmetry. For example, you can think about the Holomorphic model. It's some simple model that we wrote down, and it breaks supersymmetry. And it generates a Susy breaking scale, right? There is the energy associated with the Susy breaking. Then there has to be some interaction between the two, because we want this to generate something over here. So there has to be something that mediates the Susy breaking to the standard model. And for all intents and purposes, what you really care about mostly is this part, because this is the thing that will determine the pattern of soft masses in the supersymmetric standard model. So now, this is the part that I'm going to talk about just a little this afternoon. For now, I'm going to leave it out, but as a result of this, what we're going to get is some masses of order m tilde over here, and this m tilde is proportional to the Susy breaking scale. Okay, so that completes the story. That completes our story for the MSSM, and it's. I think you. I mean, I hope you can see that it's a very beautiful structure. I mean, it's a very beautiful theory. It's an extension. We got an extension of space-time symmetry. Lots of powerful results, and when it comes to the MSSM, what we find at this point is that we look at the correction to the Higgs mass. There is no lambda squared quadratic divergence, and instead the things that we can have here are just logarithmic divergences, and they go with the scale m tilde. So that's a very nice picture. But there's actually more than that. There's actually, supersymmetry can do even more than that. So here what we're seeing is that supersymmetry stabilizes the Higgs mass. But now suppose that we wrote down some model over here, a model that breaks supersymmetry. So what we said before is that in order to break supersymmetry, we have to put in a scale. We have to introduce some scale. In the Holomorphic model, we introduced the scale by hand. But suppose I didn't want to do that, because that's very ad hoc. So suppose I didn't put in any scale by hand, and then the theory doesn't break supersymmetry. What does it mean that it doesn't break supersymmetry? It means that the potential is exactly 0. So we're saying, suppose we don't introduce any scale by hand, then we just get a supersymmetric theory that is V equals 0. This is something that is completely clear at tree level. It turns out that if our potential is 0 at tree level, then it stays 0 to all orders in perturbation theory. When we do perturbation theory, this potential is not going to be corrected. This sounds like a very powerful result, and it is, but we'll prove it very, very easily in a few minutes. So that means that the only source of Susy breaking, if we didn't introduce it by hand, is from some non-perturbative effect. So I can only have V that's non-zero from some non-perturbative effect. So there has to be some dynamics involved. That means that the only scale, the only possible scale for Susy breaking is some dynamical scale, some sort of lambda QCD. Let me put QCD in parentheses because it's not our QCD. It's some strong coupling scale. And for a strong coupling scale like the QCD coupling scale, you know that this guy goes like your UV scale times e to the minus 8 pi squared over b g squared. So this sort of scale, just like the QCD scale, can be much smaller than your UV scale. So then what you find is that the Susy breaking scale can naturally be much smaller than the Planck scale, for example. And therefore, all the superpartner masses which are proportional to that can be much, much smaller than the Planck scale. And getting a TV-ish scale is very, very natural in this way. So if you have this sort of supersymmetry breaking, we not only stabilize the Higgs mass, we can also generate the Higgs mass at, say, 1 TeV in a very natural way. Now, this sort of breaking is called dynamical Susy breaking, or DSB in short. And it's just a statement that supersymmetry is broken by dynamical effects, by some non-perturbative effects. And if we'll see how things go, but it would be really nice to show you at least one example of this sort of breaking, but we'll see if we get there. Okay, questions before we go on? Yes?
Are we going to have like bound states in these?
I could, absolutely. Yeah, that would be very, very typical. Just like our QCD. And we'll see, that's exactly what we're going to see now.
So that's running from the flat scale down to it's exactly the same.
Exactly the same, yeah. Mm-hmm. Yes?
So you said that you're generating this one TeV very naturally.
Mm-hmm.
You have to assume something about the Gage couplings in the high scale, right?
I didn't hear the last sentence.
You have to assume something about the Gage couplings at the high scale.
Right, right. So all I'm assuming is, I mean, suppose you take the high scale to be the Planck scale, for example. So I'm taking a normal sort of coupling up there, say 1, and this very easily generates, or 0.1 or something like that, and you can easily generate a small scale. I mean, all I'm saying here is that we don't ask questions about why the QCD scale is 1 GeV. There's nothing funny about it. It's coming from, we can understand it in terms of dimensional transmutation. It's exponentially suppressed like this, and therefore it's very natural for the QCD scale to be a GeV. So the only statement here is that I don't need to introduce any very small numbers. If I wanted to break supersymmetry by hand using something like the O'Rafferty model, then if I say the only scale in the game is the Planck scale, for example, then the f that I'm putting here, square root of f, if I want all the superpartner masses to be around the TeV, in order to get electroweak symmetry breaking, I need to write down a number which is 10 to the minus 16 times M Planck by hand. if supersymmetry is broken dynamically, I don't need to do any of that. Okay? Okay, good. So, let's go on. So that concludes the MSSM part that I wanted to talk about in 5 minutes. And now we're going to switch topics completely and start talking about supersymmetry dynamics. So I started these lectures, it seems like a very long time ago, by saying that, maybe supersymmetry is really not there, but it's been useful in at least 2 ways that we're going to see. There's actually a third way, which I'm not going to talk about, but one way in which it was useful is as a sort of guide for the sorts of things that we could look for at the LHC. Another one is precisely this. You can think of it as a very nice lab for understanding dynamics, or more precisely, the dynamics of Gage theories. So this is what we're going to see now. So let's think a little bit about the example of strong dynamics that we know, namely our Qcd. That's a very beautiful and rich theory. And what do we have there? It's an SU3 Gage theory with 2 or 3 flavors at low energies, depending on whether you keep the up, down, and strange, or just the up and down. So I'm going to refer to this as a flavor. So what is one flavor? One flavor is one Weyl fermion that I'm going to take to be left-handed in the fundamental representation that I'll denote N for an SUN in general. And sometimes we'll denote it by a box, and one Weyl fermion that I'm going to be left-handed to, that I'm going to take to be left-handed in the anti-fundamental. And usually we're going to call this guy Q and this guy Q bar. And so I'm already violating my rules because I told you that bars will be exchanged sometimes with daggers, and daggers are reserved for the right-handed guys. But here, instead of, here I'm going to use bar for just the charge conjugate representation. So both of these guys are left-handed fermions. Okay, so what do we know for Qcd? For Qcd, we know that the beta function, the coefficient of the beta function is positive. I mean, that's of course, that doesn't mean very much because it depends on my sign convention, but I know that it's asymptotically free. As we go to low energies, it becomes strongly coupled. And of course, when we get to strong coupling, this is an area where we cannot calculate. So it's hard to see what's going on from first principles. So what are the, but of course, in the case of real Qcd, we have nature around us, and empirically we know that the theory confines, and that we have mesons and baryons and pions around us, and not free quarks and gluons. So what are the sorts of questions that we want to ask about strong coupling? So the very first thing, which seems kind of trivial, but it's not completely trivial, is, so this is one, what are the correct or the physical degrees of freedom? The second thing that we can ask is, so for example, in the case of QCD, we know that it's not the quarks and it's not the gluons anymore. But in principle, if we have some arbitrary theory that's strongly coupled, we don't know what's going on. So that's the first question, the zeroth order question. Then we want to know what is the unbroken global symmetry. Then we want to know what's the spectrum of particles, especially the light particles. And then we can also ask about what are the interactions of the light particles. And this kind of goes from easy to hard, right? It becomes, these questions become harder and harder from 1 to 4. And in the case of QCD, we know some of these questions, some of the answers empirically. And of course, there are some things that we can do based on lattice gauge theories that like we heard about yesterday, based on EFTs, the chiral Lagrangian, but these are in principle difficult questions. So what do we know for QCD? For QCD, for example, we know this part we already said. We know that we have the degrees of freedom are mesons, baryons, and pions. We also know for QCD that there is U1 baryon number as an unbroken symmetry. And approximately, if we set the quark masses to 0, we also have SU2 isospin, which is a very good symmetry. So this SU2 very often I'll refer to as SU2 vector. And we know some of the spectrum empirically, some from lattice calculations, but it's really getting hard, this part. Okay, there are more things that we know about QCD. So we talked a lot about the scale that's associated with strong coupling. And in the case of QCD, we have lambda QCD that's about a GeV, and I'm being very, very rough here, but it doesn't matter. And this is the typical scale of the meson and baryon masses, of their interactions, and the inverse size of all these guys. And we know, we already said this, that we can think of it as coming from dimensional transmutation. So if I look at the scale, some scale mu to the power b times e to the minus 8 pi squared over g squared at mu, this thing is a constant of the RGE at one loop, and I can call that lambda to the power b. And that's my, that's how the strong coupling scale arises from the RG. But okay, that's really nice, but you know, what does it really mean? Where is it really coming from? So in the case of QCD, we know that, or we were pretty sure, that it's coming from quark condensation. So Q bar Q is a Lorentz scalar, so it can get a non-zero VEV, and this guy's dimension 3 halves, so this thing is something that goes like a scale cubed, and so up to some number, it's this lambda QCD cubed. So in the case of QCD, the strong scale arises from the quark condensate. Okay, the next thing that we want to talk about is the global symmetry. So I already started to talk about that a little bit. Let's talk about that a little more. So what's the global symmetry? The global symmetry that we start from is the following. We have, so let me do this a little more generally. So let's suppose that I have an SUN. My Gage theory is, my Gage group is SUN, and I have F flavors. Then my global symmetry is FSUF left times SUF right times U1 that I can call left times U1 right, where this acts on the Q's, this acts on the Q bars, and again this acts on the Q's, and this acts on the Q bars. But instead of working with these two, I can work with U1 vector times U1 axial, where here the two quark, the Q and the Q bar rotate the same. So under this guy, Q goes to e to the alpha Q, and Q bar goes to the same thing, and here they sort of transform differently. Okay, so when we have the quark condensate, we break that symmetry. And let me also put indices here. So let me put an index A here, and then index I here. And so I and A run from 1 to F. So this break SUF left times SUF right to a single SUF. And it also breaks U1 vector times U1 axial to just U1 vector. Yeah.
This one that QCD, you said is 1 GV, but should be equal to the mass of the pi, I mean, to 200 MV.
So that's a good question. I said GV here stands for MEV to anything. Now for the pions of course are, if I didn't have any quark masses, the pions would be exactly massless, right? So then this scale would be the typical scale of the masses of the mesons and baryons and their interactions and their sizes and everything. Once we turn on quark masses, then we also generate pion masses, but there's another parameter that enters. Okay, so let me not talk about pion masses much more, but let me think now in the limit of 0 quark masses. So for 0 quark masses, this is all I have. Okay, so we break the symmetry like this. So then we expect F squared minus 1 Goldstone bosons from here, and another Goldstone boson from this guy. Now, of course, in our real world, we only see 3 pions. We don't see a 4th pion. And So the reason this happens, of course, is that U1 axial is actually broken. And it's broken by instanton. So classically, U1 axial is a good symmetry. Now when we look at the quantum mechanical theory, we see that there is no pion for the axial symmetry, no Goldstone boson. So it means that this symmetry is actually broken. And when that happens, we say that the symmetry is anomalous. So U1A is an anomalous symmetry. And I'm sure you've all seen this before, but let me just repeat this in case someone did not see this. So you know that the only source of breaking of U1 axial is coming from one loop diagrams. It's the famous triangle diagram. So this is J mu axial, and this is the diagram that generates it, and as a result, d mu J mu A is not zero. And what is the thing that's sitting on the right-hand side here? Up to some number, there is a g squared over 16 pi squared times GA mu nu, GA tilde mu nu. And this thing is generated by instantons. So this is coming from an instanton contribution. Let me remind you very, very briefly what are instantons. Because we'll need to talk about them a little bit. So we're looking for some solution, some background gauge field that is a solution to the equations of motion. So in particular, it has to give a finite action. Now, if I want some non-trivial solution that gives a finite action, it means that at infinity, it needs to go to zero. It needs to go to zero fast enough. What's the thing that goes to zero? If as we go to infinity, it tends to a pure gauge transformation, then it will give a finite action, because then the physical fields E and B both go to zero. So the thing that we're looking for is an A mu A that goes to a pure gauge at infinity. And it's very easy to find solutions like this if you look at some SU2 subgroup of our SUN, because our infinity is S3. And the SU2 manifold is also an S3. So here we have a one instanton solution that we can write in the following form: r squared over r squared plus rho squared. And here we're writing this in Euclidean space, u minus 1 d mu u, where u is this gauge transformation x0 plus I x dot tau over r. And r is the Euclidean r. So there is a parameter that appears here, this rho here. This is usually called the instanton size. And you'll see that indeed, as we go to large r much bigger than rho, we tend to a pure gauge transformation. And what we have here is a mapping. We have a mapping from the SU2 manifold to S3. So very clearly this is some topological object. There are different ways, there are different numbers of times that the mapping can wrap the S3, so there is some topological index that's associated with it. But I'm not going to go to any more detail besides this. Let me just mention two things, which is indeed the instanton gives a finite action, and the action that it gives, if we calculate the action for the instanton, then S, which is d4x GA mu nu is 8 pi squared over G squared. There was a question. Yeah?
So in order to get this instanton solution, you take the action, you vary the action, you get the classical equations of motion, and this is really the solution to
Yeah, that's one way you could do it. You could actually, there are some nice tricks, like you can look at, let's say that you can simplify this a little bit, but yes, I mean, that's one way you could do this. You could just check that it satisfies the equations of motion and gives a finite action. Okay. So there is one more thing that I wanted to mention regarding instantons that's going to be of some interest to us. So if we have instantons around, it turns out that we generate non-zero amplitudes which actually involve all the fermions in the theory. Or more precisely, all the fermion zero modes in the theory with some weight. So for the case of QCD, for example, I have, we said that we're working with F flavors, so we have Q1 to QF, we have Q1 bar to Q bar F, and so this amplitude is going to be non-zero in the presence of instantons, and it's actually proportional to this scale lambda, or actually lambda to the b, where lambda is the strong coupling scale of the theory. In other words, I can also write this in terms of e to the minus 8 pi squared over g squared. So you see that it's something that's clearly non-perturbative. We're never going to get something like this in perturbation theory. And pictorially, I can think of this as an amplitude where for each one of the fermions in the theory, I associate one external legs, and I generate this very higher order interaction in principle. Okay. Yeah.
Is it really non-trivial to jump from the statement of here's your instanton solution to it generates these interactions?
Now, there's nothing, I mean, everything I said here is something that properly would take a few weeks to study. Okay? But I'm just reviewing, so I think some of you must have seen this before. If you haven't, then you absolutely have to go through it properly. But I'm just reviewing some results that I'm going to need. Okay, so far for our real-world QCD. Now let's talk about supersymmetry. So now we want to talk about not just QCD, but supersymmetric QCD. That is an SUN theory with F flavors, but it's supersymmetric. So what's the new thing? The new thing here is that without doing any calculation, we will be able to guess basically all of these results without doing anything. And so the way we're going to proceed roughly is to get everything by guesswork and then kind of understand what we're getting and interpret them using these things that we just mentioned. So what's new about supersymmetry that allows us to do that? The main thing that's new is that we have holomorphy. The fact that the superpotential is holomorphic is the thing that will let us do all of this. Now, what are other differences compared to QCD? Compared to our non-supersymmetric QCD, the new things, the new elements here are that we have gauginos. So we have more fermions around. We have the U1R symmetry that's special to supersymmetric theories. And another thing that's special to supersymmetric theories is that we have lots of scalars. So each one of the fermions comes with a scalar, and so in principle we have some complicated scalar potential, and we'll have to think about that. So these are the different elements about supersymmetry. Okay. So before we really start doing something, let's do a little warm-up exercise to show you how powerful this holomorphy is. So this is just going to be a warm-up, but it's a useful warm-up because it will give us a very important result. So what we're going to do here is to use holomorphy and spurions to show that the Higgs mass, where by Higgs I really mean any scalar, does not get quadratic divergences. And in fact, so, you know, I asked you to do this exercise and show explicitly that the fermion loops and the scalar loops cancel in this example theory that we had. But here we're just going to do this very, very simply. And actually, more generally, this thing will show us also that the superpotential does not get renormalized. That is, if I start with some superpotential at tree level and I do perturbation theory, nothing happens. I get the same tree-level superpotential. Okay, so we'll go back to our very first example and use that. And remember our first toy model in the very beginning had a scalar h and one fermion psi and one fermion psi plus and one psi minus. And let's start with no Susy. And write down the Lagrangian phi, psi plus, psi minus, plus the complex conjugate. So in particular, I'm not writing down any mass, for phi. I'm not writing down any mass for phi. So this is something that I wrote down at some high scale, perhaps. And now I want to see what's happening at some low scale. So I can think about doing Wilsonian renormalization. I'm integrating out all the modes with momenta above mu IR, and I want to see what's the Lagrangian at low energies. And I also want to put in a Yukawa here. So that's a Yukawa coupling. And then at low energies, what can I have? I can have a Y prime, which depends on Y prime and the high scale that I started from. Let me call it mu UV and mu, and of course the original Y. And I can also generate perhaps an M phi squared, which is going to be a function of the same things. Okay, so in order to say more about this, in order to analyze this, let's think about this coupling here as a background field. So I want to think of it as a constant background field with no dynamics. That's very often called a spurion. And we'll see in a second why it's really called a spurion. So now I can look at my Lagrangian and look at what symmetries it has. So for example, I can say I have a U1 phi and the U1 psi plus, under which phi has charge 1 and charge 0 under this, psi plus has charge 0 under this and 1 under this, and psi minus has charge 0 and 0 here. Of course, this is not really a symmetry, because it's broken, right? If I set y to 0, I would have the symmetry, but in the presence of y, I don't have the symmetry. So now we're thinking of y as a field, so we can assign a charge minus 1 under this and minus 1 under this. And that's why we call it a spurion. When we have some coupling that breaks some symmetry, and when we set it to 0, a larger symmetry is restored, then we call it a spurion. So we assigned y these couplings, and now we can go back and think about the low energy theory. So in this low energy theory, y tilde is in principle, I can ask what's the charge of y tilde. The charge of y tilde is minus 1 and minus 1 under these symmetries. So because it has to carry these charges, the only thing that I can write down here is y tilde times some function that has, let's say, y plus some number times y dagger y plus other things. Because this thing is, of course, neutral under all the symmetries. And indeed, the sorts of things that I can get here are y times 1 plus y dagger y log mu over mu uv up to some numbers, and all sorts of things like that. Now I can look at m squared phi at low energies. This guy under this symmetry has charge 0, 0, because the mass term multiplies phi dagger phi. And so this too can be a function of y dagger y. So for example here, I can write down any combination of y dagger y. So in particular, I can have here y dagger y times lambda squared up to some number, and any combination of y dagger and y. Now let's move to the supersymmetric theory. In the supersymmetric theory, if I look at the possibility of generating the mass, so I'm looking for an M phi here. M phi, we know how it transforms under the symmetry. It's got to be a function of y dagger and the scales, but there's absolutely nothing that I can write down here because I'm not allowed to write down the combination y dagger y. So, similarly, we can ask the same thing about the coupling itself. If I look at y at low energies, again, this y can start like y, and then perhaps something like y dagger y. But this guy cannot appear because this is a superpotential coupling and no y dagger should appear there. So there's absolutely nothing that you can write down, and you conclude, I'm sorry, okay, that was the non-supersymmetric theory, but in the Susy theory, if I started with y being this superpotential, phi plus, phi minus, where now I promoted psi plus and psi minus to the chiral superfield, and phi to a chiral superfield, this guy remains exact. It simply doesn't change because there's nothing that I can write down that preserves the symmetry. Okay, so we conclude that the superpotential doesn't get renormalized. Yes? Because, okay, so this was for the non-supersymmetric theory. For the supersymmetric theory, we need to write down a superpotential. These guys are all chiral superfields now. I can put big phis for them. And y is a superpotential coupling. So because it appears in the superpotential, it cannot depend on y dagger. Because remember, I'm thinking of y as a field now. It's a coupling, but I promoted it to a field. And that's really the key. I mean, the key is realizing, and that observation is due to Seiberg, the key is to note that we can think of the couplings as spurions, and therefore only the coupling y can appear, y dagger cannot appear. Yes? If I start, exactly, so if I, very good, if I could have started here with a mass, okay, not here, but over here, I could have added m phi squared over here, and then I would conclude exactly the same. I mean, there would be no correction to this mass. In this case, I would have another spurion. I have one, y is a spurion and m is also a spurion, but it's not going to get corrected. You can go through the same analysis and convince yourself that there's nothing that can happen. No, this is the superpotential. Okay? So the thing that we get from this is the Lagrangian that we get is dw over d phi squared, and that's the usual thing.
This works for any superpotential?
Yes.
Even the one that non-normalized?
It works for any superpotential. Yeah. So it's a really, really powerful result. So the first thing that we see from here is that if we started from some mass, then the mass does not change. It stays as is in the superpotential. And any superpotential does not get renormalized. It stays as is. Now there's something very weird about this, which you could complain about, which is that we know that couplings run, right? I mean, this coupling y is just a Yukawa coupling, and the Yukawa coupling should run. And indeed, it does run. But the thing that appears in the superpotential doesn't run. So how do we see the running? In order to see the running, we have to look at the scalar potential. So where's the running coming from? So we started with a scalar potential that was canonical. It had phi dagger phi plus dagger phi plus dagger, and similarly for the minus. And then when we go to low energies, we're going to find some wave function renormalization here. So there's going to be a z phi here, a z phi plus, and a z phi minus here. That means that if I now want to work with canonically normalized fields, my physical phi is really square root is really z phi to the 1/2 times the original phi, and similarly for the other guys. And then if I look at the physical gauge coupling, the physical gauge coupling is going to be equal to the original superpotential gauge coupling times z phi to the minus 1/2 z phi plus to the minus 1/2 and z phi minus to the minus 1/2. So the running is going to show up through the wave function renormalizations. And that's actually another completely general result. I mean, the only running we have in supersymmetric theories is entering through the wave function renormalizations. There's no vertex renormalization. And you see that with holomorphy, you get all these things for free. I mean, before this realization, in the early days of supersymmetry, people worked extremely hard to show that, to basically derive all these statements. And they knew that the only renormalization you have is a wave function renormalization, but it was much more painful to derive. More questions about this? Yes.
How to prove for general superpotential? The argument you're giving seems to depend on the structure of the potential.
You could write down any example that you want, and you just basically go through the same thing. And it always relies on the fact that you can't have the coupling dagger appear. And we'll see some more examples as we go on.
Expanding the superpotential powers of phi is a very expanding.
You can look at higher powers of the fields, but essentially the question is, you're starting with some potential. You can promote the coupling to a field and invent any number of symmetries that you want, such that the coupling breaks the symmetry. That means it's a spurion associated with that symmetry, and you'll be able to show that nothing happens. And we'll see some examples. Yes?
So how does it follow that the vertices are not renormalized in holomorphy? Because I can see clearly, for example, interactions among, for example, the scalars and the fermions, but between the gauge bosons and the fermion, that doesn't seem clear.
Okay, let me not talk about, this is just at the level of the, this is the superpotential, so this is only for chiral superfields. In order to talk about gauge bosons, we need to do more, and I don't want to do that. Okay, but it's a very good question. We can talk more afterwards. Okay, so that was what we wanted to see. Okay, and now we have 10 minutes, and there's one more little remark that I want to make before we actually see something, but let me make this one remark. So very often, the thing that we'll see is the following. One of the exercises that we'll do is that we'll start from some, so this is the energy scale, and we'll start at some mu UV, some high scale, and then we're going to have some high scale theory with some high scale beta function that I'm going to call BH, and then something is going to happen. So here at M, I'm going to have some heavy fields, or the gauge group is broken or something like that, and again I have heavy fields, and then here I have a low energy theory with some below. So we'll need to do the matching between these two theories, and this is something that you've done a lot actually in both Monica's lectures and Thomas's lectures, but let's also say this for completeness here. So the thing that we want to match here is we want to match the gauge couplings. So here we'll have GH at M and GL at M. These are the two gauge couplings, and we want to match them. And we can translate this into the language of the scales lambda. So here I have lambda h to the BH, which is mu h e to the minus 8 pi squared over g squared at mu. And here I have the same thing for the low scale. And you see that demanding that these two couplings are the same at M just means that lambda h B lambda L BL is equal to M times BL minus BH lambda H to the BH. So this is what the matching translates to in terms of the lambdas. Okay. So now we want to talk, now we really want to start doing something finally, after all these introductions. And the theories that we're going to discuss here are what's called Supersymmetry Qcd, namely SUN theories with F flavors. And the first thing to note is that if you calculate the beta function coefficient at one loop, that I'll denote by V, for a supersymmetric theory, it's equal to 3n minus F. You have the extra contributions of the Gaginos, which correct this piece, and there's the extra scalars that contribute over here, and this is the result that you get, and you can work this out yourself later. And let's think about the global symmetries. So the global symmetry, let me also put the gauge symmetry. The gauge symmetry is SUN, and just like before, we have SUF left times SUF right times U1 that I'm going to call baryon number times U1 R. I'm not writing U1 axial because it's broken. It's anomalous. And the fields that we have here are chiral superfields that are labeled by Q's that are fundamentals of this. This is Q. It's a fundamental here, a fundamental of this, a singlet of this, carries charge 1 here, and F minus N over F, U1 R charge, and Q bar is an anti-fundamental here, a fundamental of this guy. I'll actually take it to be an anti-fundamental, and here it has charge -1, and this is charge, this is the same charge. Now the only thing that's funny looking here is this charge. This is the only anomaly-free U1R that I can assign. So you can check this. Basically there's the contribution coming from the Gaginos. The Gaginos carry charge 1 under the U1R, as we said, and then the only assignment that we can choose for the Q's and Q bars is this assignment, if we want them to be the same. Okay, now sometimes I'll label these guys with an index I and these guys with an index A. for the flavors, just to help distinguish between them. And the first thing to note is that if I look at the number of flavors here, and up here is 3n, for f above 3n, the theory is infrared free. So that theory is not terribly interesting to us because we know what it does at low energies, it just becomes free, but this is the big question mark. Okay. Now, the first thing that we need to think about is the scalar potential. We already said that it's very important for us to know what is V at the ground state. Is V equal 0 or is V not equal to 0? That would mean that we have supersymmetry breaking. As we'll see, in none of these examples we'll have Susy breaking. All of these examples are going to have supersymmetric ground states. And in order to look at that, we have to consider two parts. So we know that V has a part coming from the D terms and a part coming from the F terms. So essentially this is sum over all the dA squared, and this is sum over all the Fi squared. And we're looking for the ground state, so we need to look for points where V equals 0. So there are two steps to this. The first one is to find the subfield space for which Vd equals 0. That is, all the D terms have to vanish. And that part is called the D flat directions, usually. So when I have some direction in field space where all the D terms vanish, I say that this is a D flat direction. Now, it's possible, it turns out that it's possible to parameterize that. So we can parameterize all the D flat direction by the invariance, by the Gage invariance. So if I construct all the Gage invariants from the fields and I look at their expectation values, that parameterizes the D flat directions. Now if I found something such that Vd vanishes, I still need to look at Vf. So in the second stage, we need to look at Vf, and if we find that also Vf equals 0, then we found the moduli space. So the moduli space is just the subspace of the field space for which the potential vanishes. And we already know that if this happens at tree level, then it's going to hold to any order in perturbation theory. There's not going to be any corrections. Okay, so we only have 1 minute, but I really want to finally get to some example where I can show you some result, and it shouldn't take very long, so let me just do this one. But I think that, you know, having worked so hard, we really deserve some result. So let's start with the theories for f smaller than n. In a tree level, we're not going to write down any potential, any superpotential. So the superpotential is 0. Now we want to ask what is which fields satisfy VD equals 0. So you can convince yourself that it's pretty easy in this case. I mean, first of all, I can take the field Q, where here I mean just the scalars. So this is a matrix that I can write as, I can take it to have F rows and N columns. And using an SUN transformation and an SUF left transformation, I can rotate it to this diagonal form. So I have vevs V1 to Vf, and everything else vanishes. And then you can show that in order to make all the D terms vanish, I need Qt to be equal, Q bar T to be equal to Q. For this particular choice, the D terms are going to vanish. Now, I already told you that a way to parameterize that is to forget about the fundamental fields and just look at the gauge invariants. What are the gauge invariants in this case? The only gauge invariants I can make are Qi dot Q bar A. This is an SUN invariant. It's the only one I can make. And let me call it MIA for the mesons, because it looks like a meson. It's a Q dot Q bar. So this guy is an F by F matrix. And clearly I can write it, I can again use SUF left times SUF right transformations to bring it to block diagonal form. So that's the form of the meson matrix. And these are the D-flat directions. So I can label the D-flat directions by these vevs of the meson field, and we see that this W is essentially just the square of the V. Okay. Now, what I know is that the superpotential is 0 to all orders in perturbation theory. So this is the, to all orders in perturbation theory, this basically gives me the set, the moduli space of the theory. The potential vanishes exactly along these directions. But now let's see what we can do non-perturbatively. So now we can ask what happens to W, what happens to the superpotential at the non-perturbative level. So the question is there anything that we can write down? So the superpotential needs to be invariant under SUF left times SUF right. And of course, the superpotential depends on these mesons, the MIAs that we wrote down there, that parameterizes the moduli space. So the only thing that's invariant under this that I can write down is the determinant of M. That's invariant under the symmetry. Then let's see what else I have. I have U1 baryon number. That doesn't help me very much because M carries charge 0 under U1 baryon because it's Q times Q bar. But then I do have U1R, right? So U1R, the charge of M under U1R is 2 times F minus N over F. And therefore the determinant of M carries charge this to the power F. So it's just 2 times F minus N. Now, remember that under the U1R, W should have charge 2. So that means that the only thing I can write down in W, the only superpotential I can write down is the determinant of M to the power let me write it as minus 2n minus f over f. Did I get this correctly? No, I'm sorry. I screwed up. So the only thing that I should write, the only thing I can write down is this to the power minus n minus f. Now there's another thing that I know. I know that W has dimension 3, and this doesn't have dimension 3. The only dimensionful parameter that I have at my disposal is the strong coupling scale of the theory. So I should put in enough powers of lambda to give me the right dimension. And it's very easy to show that the only thing that you can write down is lambda to the 3n minus f divided by det m to the power 1 over n minus f. And up to some number, this is the most general form of the superpotential. So what we did here is we derived the exact superpotential for this set of theories which are strongly coupled. And that's completely non-trivial. Now, you could ask, of course, very nice, but maybe this number here is 0. Totally fair question. What we'll see next time is that it's actually non-zero. So this thing is actually generated, and I'm not gonna have time to talk about prefactors, but all the prefactors can be determined in everything that I'm gonna say. So we know the full thing, including the prefactors. And there's one more thing that should make you happy, which is that without doing anything, what we got here was exactly lambda to the b. Okay, this is 3n minus f is the beta function coefficient. So we got lambda to the b, which is the natural thing to expect to show up. So that works out very nicely. So I think I'll stop here and go on with this tomorrow.